Morning, everyone. Hope you all can hear me properly. This is Vijay here. I've been working in telecom industry for the past 10 and a half years now. I started my career with LTE, which is the 4G technology, and it was in the RAN side, and then I moved to the EPC, which is the core part, and then I came back again to the RAN part, the radio access network in the 4G LTE, and in the last close to about 1 year I've been working on 5G. So this session, as Ms. Sakina said, it will be about what is 5G and how it is better than the legacy telecommunications or the LTE. We compare it basically with the LTE. As we all know that LTE is already there in India. We all use 4G in our phones. And what will be so special about 5G? What is the need? And when will it be launched in India? And what are the customers that are working on this? What are the companies that are working on 5G right now? And I mean, what role will it play in our daily life? That will be the agenda of this topic. So without further delay, let's get in. As you all know, LTE started somewhere in 2008, 2009, and then we had the 3GPP release. 3GPP is the group which categorizes the fundamentals for each technology. For example, we have LTE and we have LTE Advanced, we had LTE Advanced Pro, and now we have 5G. Even in 5G, there are multiple releases, right? So we started with release 15, as you see, but then we have release 16 now available. Release 17 is also going to be out in December or probably early next year. And every release we are slowly able to make some changes and probably have more modifications and make some better advancements of the same. Okay, so in LTE, if you see, we could reach a maximum of about 300 Mbps, and that was with downlink 64 QAM, which was the modulation. And the latency, as you see, was about 50 milliseconds. This is the end-to-end latency. Okay, from the time we started, we start a RATCH process until the end of UE getting attached. This was the latency. Okay, the channel bandwidth was 20 megahertz. It started from 1.4, 1.435. The max bandwidth was 20 megahertz in case of LTE. And in LTE Advanced and LTE Pro, if you see, the throughput increased. The only reason, because the bandwidth is still the same if you compare LTE versus LTE Advanced versus Pro. But why the throughput changed was because we had downlink 256 QAM, which was a even better modulation as compared to LTE, right? And we also had number of carriers. If you see the last but one, so the LTE Advanced has number of carriers as 5, and the LTE Advanced Pro has number of carriers as 32, right? Which means that you can add up the number of carriers, and that used to increase your total peak throughput of the cell. Okay, we'll talk about what the carriers are and how it will be beneficial in 5G as well. Okay, and the number of antennas in LTE were 4. We could do max 2 cross 2, or at best we could do 4 cross 4. In LTE Advanced, we had increased it up to 8 and then 32 and so on. However, these antennas and the number of layers, what the numbers that are suggested here, are for the over-the-air transmission, right? When we do it in the cabled environment, mostly we stick to 4 cross 4 or 8 cross 8, which means we do 8 layers or 4 layers. Okay. Now 5G, if you see, it started from release 15, and the target is to get more than 10 Gbps with a latency of 1 millisecond, right? And it will not be like you get one technology and you have everything in the same thing. So there are multiple things in 5G. So we have like EMBB, we have URRLC, ultra reliable low latency, and that's where we talk about the low latency, which is less than 1 millisecond. And then EMBB is the enhanced mobile broadband, where we talk about traffic basically getting more than 10 Gbps. And here carriers are 16 layers. It says LTE plus NR. I will talk about this in the next few slides, where we have carrier aggregation between, we can have it between LTE and an NR, or we can have it between two different frequencies in the same LTE or in NR itself. Okay. So that is basically to increase the capacity versus coverage. So this is the 5G is going to bring up all this. And if you see the channel bandwidth for 5G, it is up to 500 megahertz. We have two frequency ranges in 5G. So let me go to the next slide and probably we can have more detail. Yeah. So the need for 5G came because we already had 4G. However, we wanted more speed. The latency had to be lesser. Okay. And then in LTE advanced, we did get higher speeds and low latency. But in 5G, we are not just talking about the mobile technology. We are talking about the whole lifestyle being changed. For example, the 5G combined with IoT, right? Internet of Things, or if you combine it with AI or machine learning or something, it might get into your daily devices, like the number of applications that are connected to the internet, the number of appliances that you have at home that can be connected to internet. And we talk about smart cities and all that, right? So that's where the need for 5G came into picture. Okay. Basically, we needed more reliability and then faster speeds and then more data, basically. And then the coverage and capacity is where we will do carrier aggregation and other topics. Now, let me get into the most important slide here. Yeah, so this is exactly what I was talking. So 5G is basically about your EMBB, URLLC, and MMTC. So let's talk about EMBB first. So EMBB basically means your enhanced mobile broadband, and enhanced mobile broadband is nothing but right now we saw the data throughput, right? The cell peak data throughput, where we mentioned that for 5G we need to get about 10 Gbps, right? So how are we going to achieve that? With LTE, we had a bandwidth of 20 megahertz, and 20 megahertz means there is a PRB, right? Physical resource blocks, which are allocated for the downlink data. So that physical resource block maps to 100 in case of 20 megahertz. Okay. There is a calculation for that. I'm not getting into the calculation of how we arrive at the PRBs, but let's assume that for LTE, 20 megahertz gets us the 100 PRBs. Now we need to increase the capacity. So we increase bandwidth. Okay. So in 5G, as I told you, we have FR1 and FR2. So what we say about FR1 is the frequency range 1 and FR2 is frequency range 2. Okay. So with those two, I'll cover more about FR1 and FR2 in the next slide. But with that particular thing, by increasing the channel bandwidth and by increasing the modulation and the subcarrier spacing, we will be able to get more throughput. So when your system capacity increases, obviously you can handle more throughput, more number of users, and then you can have a better spectral efficiency. And for example, we talk about triple play, right? One, if you have a handset and if you want to do a video call, but on the background you want to download some applications over FTP or probably even a video, right? 4K video, if you want to download it, that will keep going on in the background. However, on the foreground, you will be doing a video call or a voice call, right? So that is where we say triple play or whatever. And then we have extended coverage. So regarding the coverage, talk in the next slide, because as the frequency increases, the coverage decreases. Okay. But in order to increase the coverage, we come up with certain things like carrier aggregation or combining the carriers, component carriers, 2CA, 3CA, and so on. Now let's talk about URLLC. So URLLC is basically your low latency, and we discussed in the previous slide that we should be able to see less than 1 millisecond latency. Okay. Actually, in some cases, they even talk about microseconds, right? Even lesser than 1 millisecond, and probably end-to-end call, we need to have some buffer. So we keep it like, say, 50 microseconds, 500 microseconds, and so on. Okay. Why is this important? Because when you have low latency, you can extend this 5G in a lot more applications like hospitals. Okay. And then where you need to monitor something periodically without any delay. That is where, for example, in before 4G, before LTE came into picture, we were not able to view live videos which were 720p or 1040p, right? Pixels. But now we are able to do with respect to 4G. But still, sometimes we observe that it stops in between, and then there is a delay, there is a buffer data, and then it slows down. But all that will not be there in case of 5G. And that's the reason this 5G will be introduced across the telecom technologies. It will not be only for phone or for a TV or iPad. It will be into hospitals, it will be into smart cities, it will be into, I mean, probably we can have all the home appliances connected with IPv6, and then we can control all these applications with your phone. You will have multiple apps. Right now, if you see, everything is application based. So that is basically your URLLC, that is ultra reliable low latency communications. Here, when the latency becomes low, obviously the reliability will be high because the packet loss will be lesser. Okay, the jitter, packet loss, all those will be lesser. And then, for example, what we had in voice call, in voice over LTE, right? In LTE, we had something called voice over LTE, and that had very less jitter and packet drop. And but we are even looking at ultra reliable low latency, which will be like much more lesser latency, lesser delay, and lower packet losses as compared to the LTE. And then location precision. This will also be used in, for example, GPS coordinates, or if in case we need to find out where a particular accident happened, right? Something immediately needs to be happen. If there is an issue which is happening within 30 minutes, can we get all the details? Can we get the coordinates? And that's where we need the ultra reliable latency. The third point is MMTC, which is the machine type communications. And this can be, I've written at V2X because it can be vehicle to vehicle. It can be vehicle to anything, for example. So for example, there will be a chip which will be placed inside a car, and that will be a 5G chip. And then that particular chip will be able to communicate with either different vehicles, or probably if it is like a self-driving car, then it will automatically look for the next traffic signal, or it will show us the next exit that is going to be available, or the next if you want to take a break, probably the next restaurant, or the next place where you can halt your car, and so on, right? Basically, it will be like communicating two devices between each other, and then how to gain maximum advantage with 5G coming into picture. And that's where we will need low complexity, high connection density, because you need connectivity to be there all the time. You cannot lose connectivity there at all, okay, even for a small time, right? And then extended coverage, and then the energy optimization. All right, this is basically the MMTC. All right, now let's go to the next slide and probably look at a little bit detail of what is happening. Yeah. So I gave a brief introduction of FR1 and FR2. So FR1 is the frequency range 1, and FR2 is the frequency range 2. What is so much different about these frequencies is FR1 is mostly sub 6 gigahertz. Okay. So LTE, if you see, we already have LTE deployed in India. We have our operators, Jio, Airtel, Vodafone India, now VI, and all these operators are operating either on 700 megahertz or 2.1 gigahertz frequency. There is also an 1800 megahertz band, 1.8 gigahertz band where they operate, right? These three are the mostly used frequencies in LTE. In case of 5G, we will probably have 2.4 gigahertz. Anything below 6 gigahertz, we call it as FR1. Okay, this is standardized by 3GPP, as we mentioned earlier. Now, within FR1, there are a lot of frequencies, but in India, we might have 2400 as the primary one, which is TDD. But if you go in other EMEA or APAC or US, you might be able to see many other different frequencies, and each frequency range will be mapped with a UE band. Okay, and that particular UE band has to be supported by the UE to get connected, right? For example, back then we had CDMA phones, and if you take the phone out of India, you might not have signal at all, right? Because that supports only single band. Now all our phones have multi-band support, and basically what that means is it can support multiple frequencies. That is what is FR1. Okay, and FR1 mostly is done by cabled environment in the lab testing. Okay, FR2 is higher frequencies, which is most probably 26 gigahertz, 29 gigahertz, right? Which is like huge. The problem with FR2 is since the frequency increases, the coverage will be lesser. So for example, if you have a big circle which caters to about say about 4 kilometer radius, okay, that 4 kilometer radius is accessed by 700 megahertz, and then if you increase to 2.2 gigahertz, then the coverage will reduce probably by a radius of 2 kilometers. And then if you bring in 28 gigahertz, it might be few hundred meters, that's it. Okay, the reason is because when your frequency increases, your coverage reduces, but within that coverage you can get very high throughput. Okay, so this is where the network optimization or the network planning team will come into picture. For example, in any of the business districts, for example, let's say Mumbai or New Delhi or in Bangalore, where there are a lot of offices, right? The network planning team will ensure that there are more higher frequencies deployed. Operators, I mean the carriers, are deployed in those regions so that more throughput can be given to the attached users. Okay, if we are looking about coverage, then probably there will be one or two towers which will take care of probably one district, but they will not be able to give huge data. They will just ensure that, okay, I can give coverage to like 6 kilometer radius, but I can handle 1000 users, but I will not be able to provide them more throughput. They'll just stay connected, and probably they will be able to download something with a lesser speed as compared to the higher frequencies, which will be able to provide mobile broadband or ultra low latencies for probably all the connected users, right? So wherever the density is high and the usage is more, for example, a stadium, right? A cricket stadium or a football stadium, where there are a lot of people, audiences are seated around, and everybody wants to use their mobile phone to do a video call, or they are taking a high definition video and they are uploading it on any of the social media channels, right? All those places we need to deploy a higher frequency range. Okay, now currently what is happening is in the lab we are testing FR2 over the air. We can test FR2 with cabled environment as well, but it has to then, I mean, you cannot transmit a 28 gigahertz over the air, right? I mean, over a cable, right? It will be too much. So what we have to do is we have to have a converter so that that frequency gets converted to a lower frequency, and then up converter and down converter. Probably you might have heard these terminologies. We will need to use that in the lab environment, but over the air will be the best thing for effort. So next, moving on to the topology. So for 5G, we have NSA and SA. So NSA is non-standalone and SA is standalone. So what does non-standalone mean is we already have 4G deployed in India, right? So we can use the same 4G as the primary anchor and then have the 5G as a secondary carrier group, okay? So there will be a message after your LTE attached, the UE gets attached. There will be a SCG message, secondary node getting added, and that will be the 5G node. In this case, what will happen is you can have the data downlink path go only on 5G. Okay, I mean, it can be on either LTE or 5G, but the advantage on NSA is your LTE is already there. It's already deployed. You only have to have another part of 5G, which will be attached as a secondary carrier. Okay, but the uplink will happen only on the LTE channel, which means LTE will be the primary carrier, and then your secondary carrier will be 5G, and that will be your downlink data.